Welcome back. We had been talking about general computer architecture, hardware and software. At some point though, we have to nail down one device so we can study its details. And so in this video, we're going to begin investigating the MSP430, which is manufactured by Texas Instruments. So the block diagram on the right should look familiar. We've seen it before, but now it's got a little bit more detail. For example, notice the ALU has status bits Z, C, V, and N, which we'll discuss in this video shortly. Also note that the bus system includes technically 20 address bus lines for selecting addresses, 16 data bus lines for moving data to and from memory, and also observe their directions. The CPU uses the address bus to access the memory locations, so the address bus points from CPU to memory. The data, on the other hand, moves both ways depending on if the CPU is to read or to write data to and from memory. I said technically the device has 20 memory address bus lines. However, usually when we address, we will use 16 address lines, and the other 4 will be 0. I'll elaborate that on in just a little bit. At the figure at left is the MSP430, which is the small chip at the center of the red board. The rest of the board is called the development board, and its manufacturer, Texas Instruments, refers to it as the launch pad. It contains peripheral devices to interact with the MSP430. There are different models of MSP430 and many different data sheets for each of these models. The one shown in the figure is the 6989. Data sheets retrieved online from Texas Instruments may be for the MSP430 and contain general information that applies to all of these devices in the family, or they may be for the 6989 specifically, which will of course have more details for that specific device. So let's now move a little bit deeper. Now, we've used the term memory map before, which means everything external to the CPU has a specific, unique address, utilized by the CPU to reference the data there. For example, the CPU may write data to a specified address or read data from a specified address. Now, at each address is 1 byte, or 8 bits. These bytes are not independent, however. You should think of the bytes in pairs or groups of 16 bits. The MSP430 is a 16-bit CPU, and by default, words of 16 bits are accessed, unless specified otherwise by the programmer. Entire 16-bit words are accessed at even addresses, typically expressed in hexadecimal, which is indicated by the H appended to the end of the address. So when someone says 8,000 in this context, it means 8,000 in base 16, not decimal 8,000. So for example, word 0 resides at address 0. Word 1 resides at address 2. Note that word 1 does not reside at address 1, since address 1 contains data from word 0. In a previous slide, we noted that the MSP430 technically has 20 address lines, but for now we're only going to be concerned with a lower range, the lower 16 address lines, and the upper 4 will always be 0. So because 4 bits encodes 1 hexadecimal digit, you see that we have 5 hexadecimal digits there on the address. That most significant digit is going to be a 0 usually, leaving us with 4 hexadecimal digits. If we used all 5 hexadecimal digits, well, 16 to the 5th is 1 mega addresses, or 2 to the 20th. But if we fix that most significant digit at a 0, then we have 4 hexadecimal digits to play with, and 16 to the 4th is about 65,000, and that would be 2 to the 16th. So if we don't understand this, how many unique addresses we get, let's consider that a single address line can be 0 or 1. So it can specify 2 addresses. One address line specifies 2 addresses. 2 address lines, then, by the same logic, can specify 4 addresses, 0001, 1011. In general, n address lines can specify 2 to the n unique addresses. So 16 address lines specifies 65,536 unique addresses, and 20 address lines specifies 1 mega addresses. And then since it takes 4 bits to represent a hexadecimal digit, it takes 16 divided by 4, or 4 hexadecimal digits, to specify the addresses if we fixed the most significant digit to 0. Okay, so let's move on. Another way to consider the data is by bytes instead of words. In this way, each byte resides at each address. So for example, byte 0 is located at address 0, and byte 1 is located at address 1, and so on. But we now know that the bytes are not independent, as 2 bytes comprise 1 word. The storage is such that the upper byte, that is the most significant byte, has an odd address, and the lower byte, that is the least significant byte, has an even address. So for example, the byte at address 1 here is the most significant byte of word 0. The byte at address 0 is the least significant byte of word 0. Now let's shift focus to the CPU and its registers. The MSP430 contains 16 total registers, each 16 bits wide. Often we will want to store addresses in the registers, so it makes sense that registers are the same width as the addresses. Now, technically they're 20 bits wide, but again, we're saying that we're going to fix the most significant digit of the address in hexadecimal, so that leaves us with like 16 bits. And for now, we don't need to understand why. Maybe we just think that maybe we just consider it to really be 16 bits wide, and maybe we, in the back of our minds, store that actually it's 20 bits wide. Anyway, the first 4 registers are denoted as R0 through R3, and they are special purpose registers, whereas the next 12 registers are denoted R4 through R15, and they are general purpose. So let's look at the special purpose registers in a bit more detail. The first register, which is denoted R0, is the program counter, which we will abbreviate as PC. The program counter is the first register, and perhaps the most important, as it holds the address of the next instruction to be executed. Now we see why the registers must be at least as wide as the addresses, right? Because they can store address information. So it's got to hold that address, in this case, the next address to be executed. The second register, R1, is the stack pointer, which we will denote as SP. It's used with the stack to dynamically allocate memory, which we're going to cover later. The third register, R2, is the status register, which we will denote as SR. It contains flags that are asserted by the arithmetic logic unit under special conditions. We will elaborate on this in just a little bit. The final dedicated register, R3, is the constant generator, denoted as CG. This is used by the CPU to speed up instruction execution, but it's not something that we really need to be concerned with at this time. Just know that R3 is there and it's dedicated. We don't have access to it as a programmer. Now, going back to the third register, R2, which is the status register SR, it contains 4 bits that we need to be aware of right now. All right, these bits are V, N, Z, and C, or bits 8, 2, 1, and 0, respectively. Bit V is the 2's complement overflow flag. When the ALU, the arithmetic logic unit, performs a subtraction or addition with negative numbers, the overflow flag is asserted when overflow occurs. The word asserted here means equals 1. V is 0 otherwise. Bit N is the negative flag. When the ALU performs a subtraction or addition with negative numbers, the negative flag is asserted, if the result is negative, and is 0 otherwise. Bit Z is the 0 flag. When the ALU performs a computation, the 0 flag is asserted when the computation results in 0. Z is 0 otherwise. So you can see we might want to know when a calculation gives us 0, or gives us negative, or gives us an overflow. Bit C is the carry flag. We might want to know when we have a carry out, because the ALU performs an addition or subtraction, and remember, subtraction is an addition of a 2's complement. The carry flag is asserted when a carry out occurs at the most significant bit. Otherwise, C is 0. All of these bits are reset to 0 when the MSP430 is reset. Now, the MSP430 contains many, like a plethora of peripherals, which include some here. The digital I/O that can be programmed to function as inputs or outputs. Importantly, each port has a pull-up or a pull-down resistor that can be optionally utilized. Each port is 8 bits wide. It's got a serial I/O to support common communication protocols, including UART, SPI, and I2C. The MSP430 has 4 binary timers that run independently from the CPU, so programmatic action can be taken depending on the value of these timers. It also has analog to digital and digital to analog converters to increase its applicability, so it can handle many different scenarios by accepting analog signals and outputting analog signals. Digital too, of course. I mean, it's a digital system, so it has no problem with digital. And it has a clock system which synchronizes activity and facilitates synchronous circuitry. Okay. So in this lecture, we looked at some of the hardware details of the MSP430. Next time, we're going to look at the software. Thank you.